Today, we're just going to extend what we were talking about the last couple days, the last couple times we've met here and talked about math. We're going to look at the situation today where what if when we write an expression using rational exponents, we end up with an improper fraction, meaning a fraction where the numerator is bigger than the denominator. Let's click them all closed. Everybody up here, please. What do we do with that? Okay, now let's keep in mind when we are simplifying radicals, our goal is always to get as much out of the radical as possible, right? We want as big an outside part as we can, as minimal an inside part as we can. So could we do something here? Well, yeah, we could. We could. Now, I've got a really good trick for this. This is so useful. This is one of the things that when people go on to college, this is something I hear back, this is really handy. Okay, it's a great way to think about it. The alternative is kind of cumbersome and complicated. All you have to do is just take that improper fraction where the numerator is bigger than the denominator and write it as a mixed number. Okay, if you write it as a mixed number, like what would 11/3 be? How do you know? How do you turn that into a mixed number? How would you turn 11/3 into a mixed number? Okay, good. So 3 goes into 11 how many times? 3. So that's the integer part, right? We get 3, and how much is left over? What's the remainder? It goes in 3 times with how much remaining? 2. So the remainder is what goes over the denominator. So it remains over the denominator 3, right? So we end up with 3 and 2/3. Well, what does 3 and 2/3 really mean? When we write a mixed number like that, 3 and 2/3, it's not 3 times 2/3. What is it? Like 3 and a half. Yeah, it's plus, isn't it? Right? Because 3 and a half is 3.5. It's 3 plus another 0.5, right? So it really means 3 plus 2/3. Now, you don't have to write all these steps down. We'll be able to make a shortcut out of this, and we'll go through an example in a second, and you'll see that. Uh, but it really is 3 plus 2/3. Now, we have a property of exponents that we use all the time that relates to that. How do we end up getting, like we use one all the time where we end up, the result is a to the m plus n. Where does that come from? Where we're adding exponents. When do we add exponents? When we multiply well, like bases, right? So like if I have powers with like bases, I mean, you guys you're thinking fractions. We got to turn this, we're going back to properties of exponents for a second, right? So this will look familiar. A to the m times a to the n, you'd all tell me is a to the m plus n, right? Because what's our rule? When you multiply powers with like bases, you add the exponents, okay? So, well, we'll just go in the opposite direction this time. We're going to start here and move back in that direction, right? So if we have x to the 3 plus 2/3 power, we'll just split that up into x to the third times x to the 2/3, right? Make sense? And then what does that become? Well, x to the third power, that doesn't have a fraction in the exponent, so that does not need a radical, right? That ends up being the outside part of our radical when we turn this back into a radical, right? So we get an x to the third outside, and then inside, what do we get? Well, x to the 2/3, we already know that the denominator is what corresponds to the type of radical it is. It's the index, right? So we know we get a third root, and the numerator just tells us the power of the base inside that root, okay? Get the idea there? So how could we make this quicker? Well, really all we've got to do is go from x to the 2/3 down to x to the 3 and 2/3, and we could immediately convert that to our answer, right? Because we know that the integer part goes outside, the fraction part corresponds to the inside, okay? Give me 1 to 5. How are we doing? Does that make sense? Okay, we're getting there. We need to practice though. Let's practice one of these. Okay, so how about this guy? What am I going to do first here? What do I do? Subtract what? You're right. Okay, good. So I'm gonna, when I divide like bases, I subtract exponents, right? So good. So we start off with, we're gonna get x to the 17/5 minus 8/5, which is x to what power? The 9/5. Okay, so our goal is to convert that into a radical, right? Now, am I gonna need to turn that into a mixed number or not? Give me thumbs on that. Mixed number? Yeah, I have to, right? How do you know? Yeah, the numerator's bigger than the denominator, so it's got to be a mixed number, right? So we're going to write that then. We have to write that as a mixed number, which means I'm going to have an outside part and an inside part to my radical. Okay, so what's that going to look like as a mixed number? What is 9/5 as a mixed number? 1 and 4/5. Okay, so then what's my outside part going to be here? Andre, what's the outside part going to be? X to the 1, right? Yeah, right. Remember how that works? So then we just get x to the whatever the integer part of that is. And in this case, it's x. Last time might have been an a or something. I can't remember what it was. But anyway, it's an x this time. Well, I guess it was an x last time. So outside we get x to the 1. The 1's invisible. We wouldn't really write the 1. But just so you can see, there's the 1. Now, what kind of root do we have here, Persephone? Good. Fifth root, isn't it? Good. Because of that, we've got a 5 in the denominator. So it's a fifth root of what, Kyler? What goes inside? Just a 4? Like that? Just a 4? X to the 4, right? That's going to be the power of x that's inside. Okay, now give me 1 to 5. How we doing? Okay, all right, we're getting there. Jump to the boards and try that one real quick, and then we'll talk about it. Let's talk about this one briefly. Just a couple things worth mentioning. Okay, people did a great job on this. So first of all, we would turn these into rational exponents, and you get that, like, when we have them written as radicals, who would know what to do, right? I mean, it's complicated. The radicals are very clumsy to work with. It's way better to put them in terms of, to rewrite radicals in terms of rational exponents. And then the algebra is easy. We just lean on the properties of exponents, right? So this one gives us y to the 3/30. This one gives us y to the 41/15. Okay, and now when there's a temptation here. There's a temptation to reduce that fraction and make it 1/10. Now you can do that. It's fine to do, but ultimately we're going to be combining those into a single base, right? When we multiply like bases, we add the exponents. So this is going to equal y to the 3/30 plus 41/15. Well, we're going to have to get a common denominator when we add the fractions. What's our common denominator going to be anyway? It's going to be 30, right? So, you could reduce this, but you're going to have to turn right around and convert it back to a 30 anyway, aren't you? Right? So kind of keep an eye on that. What would I have to do to the second fraction to get a common denominator? Good. Top and bottom by 2. And we end up getting then y. I've got a common denominator of 30, and I get 3 plus 82, which gives me y to the 85/30. Okay. So we could write that as a mixed number, y to the, 2 and 25/30. okay, which is the same thing as, whoops. Come on, that's y squared times y to the 25/30th, right? Or plus, does that make sense? What could I do with the 25/30th though? I could reduce it, right? And that's another thing that would be difficult to see. If you hadn't turned this into a rational exponent, it would have been difficult to see that you could have reduced those numbers. When those numbers show up as a power inside a fraction and an index of a radical, that's confusing to know if you can reduce those or not, right? But now it's easy. We just use properties of exponents. So we could reduce this whole thing to y to the 2 and 5/6 power. And so that's going to turn that y to the 5/6 into what? How would I write that? Sixth root of y to the 5th. There we go. Okay, good, good, good. All right, let's try something a little bit different now. So this looks complicated, right? Doing something like this looks terrible, probably looks scary. Okay, I'm going to make it simple. I'm going to make it simple. Now, when you're dealing with a radical that involves a product of a coefficient and a bunch of different powers, so maybe we have multiple variables being taken to exponents. It looks terrible, but the process is simple. All you have to do is break it into pieces. Yes, sir. No. You guys want that as a printout? I can. When I'm done, I'll print it out if you want it. Yeah. But it'll be in the notes too. I've been updating plan book every day, right? So you know where to see this stuff, right? Okay, so um, we could break this into parts because everything, the radicand, everything that's inside the radical, because they're products, I could think about that as being the product of four separate radicals. I don't have to physically break it apart into four separate radicals, but I want to think about it that way. First of all, let's think about the fourth root of the coefficient 288. Well, what would I do? Fourth root of 288, that means we've got to go back and use our saying. We got to use a factor tree. What's our saying become for a fourth root? Okay, so quads go out, everything else stays in, right? Okay. So then if I used a factor tree and I factored that whole thing, here's what I would get. I would get a string of 5 2s multiplied by 2 3s. Okay. So what's that mean then? Well, it means I've only got a quadruple 2, and then I've got a leftover single 2 and double 3. Okay, but those would stay in, wouldn't they? So then my outside number becomes a 2, and my inside number becomes 2 times 3, which is 18. Okay, check that one off. So the number's taken care of. We know which part of the fourth root of 288 gets to go out front and which part stays inside. Now we're just going to do the same thing for each individual variable. Big deal, right? I've got fourth roots, so I just know that x, the fourth root of x to the 7th, well, that's going to turn into an x to the 7/4. We know how to deal with that. We just did. X to the 7/4. 7/4 becomes 1 3/4. So I get an x to the 1 outside, and I get an x cubed inside my fourth root, right? Okay, now what about the y to the 1? Do I even really need to do a trick for that one? No, this is going to stay there, right? Isn't it? Because, I mean, think what would happen if I turned that into a fractional exponent. That becomes y to the 1/4. Well, I don't even need to write that as a mixed number. It's done, right? It all stays inside. So because the y is not to a power 4 or bigger, right? Its exponent is less than 4. The y is just going to stay put. Just going to stay there. Don't have to do anything to the y, okay? But the z has a power of 18, which is bigger than 4, right? So we need to turn that into a mixed number. I get z to the 18/4. Okay, now here's a question. 18/4 reduces to 9/2. Should I reduce this? How come? Yeah, because look, we know that we're going to want to get a fourth root, right? So we need to have a 4 on the bottom, don't we? We need to have a 4 on the bottom of everything if I want to contain those under one radical, which we want to do. We don't want to split this up into separate radicals. That would not look very simplified, would it? Right? So here's the rule. Only reduce rational exponents if you can reduce all the exponents to the same denominator, right? If any of them can't be reduced, don't reduce any of them. And typically, usually, I mean, how do you say usually in math? It can always happen, but typically you can't usually reduce those, if you got a whole bunch of them at least, right? But if you can, I mean, that's fine. If these had all been, what if I could have reduced all of these down to 2's? Well, that's fine. Then I can reduce them all to 2's. Okay, that's good. So in this case, my 18/4, I'm just going to turn into 4 2/4. So that's going to give me a z to the 4th outside and a z squared inside. And now all I've got to do is combine the product of all the outside parts outside of my radical times the 4th root of the product of all the inside parts. Okay? No big deal, right? Try one. Try that one. And before you start, let me ask you a quick question. If I have an odd root of a negative number, what happens to the negative? No. If it's an odd root, if it's an odd root of a negative, we might as well just put it out front, right? Because like what's the cube root of -8? No, -2, right? What's the 5th root of -32? The 5th root of -32. No, it's -2, right? The odd root of a negative number is always going to be negative. So you might as well just, if you have an odd root of a negative, one thing you can do to make it easier is pull that negative outside. Even if nothing else goes outside, at least the negative could be outside, right? Okay, go. Oh, okay, so first things first, right? We could take this negative, that goes outside, and then 243, that is just, yeah, 243 is 3 to the 5th, isn't it? Right? So if we were to make a factor tree out of that 243, we're just going to get, so how about that? We just get a quintuple 3, so that goes out. So that part's good. Quintuple. What's that? 6 is called a sextuple. Mm-hmm. Septuple. Mm-hmm. Yeah. Yep. It is. Okay, we're getting a little off topic here, though. Let's finish this up first. So, would everybody agree then that the x part of this is going to be a 9/5 power, isn't it? Right? Because we got an x to the 9th, and that 5th root makes it a 5 on the bottom of the fraction, right? So x to the 9/5 as a mixed number becomes what? There you go. X to the 1 and 4/5. So what's that telling us? Well, that's telling us then, oops, forward, there we go. That's telling us that what goes out front? X to the 1. So we get 3 times x to the 1. What goes inside for the x's? Good. X to the fourth, and we know it's a fifth root because of the denominator, right? Okay, how about the y? The y just stays there, doesn't it? Right? Because it's a y to the 1. So we know that's just going to stay put. Y to the 1/5 just stays put. That's our answer. Okay? Good? All right. Have at it.